Hello everyone, I'm Wang from Huazhong University of Science and Technology. Now I will present Mlog, multi-log write buffer upon ultra-fast SSD read. Redundant array of independent disks, read for short, can combine multiple storage devices to promote overall storage performance and reliability. The read architecture is categorized into various read levels. The non-parity reads include the striping-only read 0 and the memory-only read 1. Moreover, parity-based reads, including read 4, 5, and 6 levels, incorporate redundancy data called parity chunks to tolerate disk failures. However, parity-based reads need a more complex write processing method called read-modified write. For full stripe write, where all data chunks of a stripe are written, the read system generates all new parity chunks at once and then writes both data and parity chunks into corresponding disks. Differently, for a partial stripe write, where only a subset of the data chunks of a stripe are updated, only after its old data and parity chunks are read from the disks, the stripe is updated and then written into the disk again. This induces numerous actual disk accesses. This read-modified write nature of partial stripe writes makes them costly. The read buffering mechanism is a popular and mature solution for parity-based reads to elevate the overhead of partial stripe writes, which can be roughly classified into two types as data buffering and parity logging. The data buffering approaches, like the linked read journal model, absorbs all data updates of read stripes into the buffer. It flushes them to the primary read array after the data could be merged into a full stripe write, thus speeding up write performance by eliminating the performance-degrading partial stripe writes. Besides, parity logging is another read buffering method that only buffers parity updates in a logging manner, while data updates are in place writing to the primary array simultaneously. Today, the read system could utilize modern SSD devices to deliver higher bandwidth. The left figure shows the write performance boundaries of SSDs that were introduced over the past 80 years. We can observe that SSDs could provide higher write throughput. Even only one SSD can provide more than 10 GB per second throughput. Besides, modern ultra-fast storage like NVMe SSD has better write scalability to support concurrent I/Os. As the right figure shows, the throughput of SSD is positively correlated to the number of accessing threads. It indicates that a multi-threaded access pattern is essential to reap the intra-parallelism of SSD. The increased performance of underlying storage motivates us to revisit the read buffer designs. The question is, as the performance of SSD-based reads increases, will the existing read buffer mechanism still be able to provide higher throughput than their primary read? We measure the read journal and the PPL performance running on three types of SSD devices whose characteristics are listed in this table. We first deploy 6 SSD devices to construct a row RAID 5 and measure its performance as a baseline. We enable partial parity logging in empty read by using the empty admin option. Besides, we implement the read journal by deploying an additional SSD device and a RAID 0 device consisting of 6 SSDs as a buffer device upon the main array respectively. The read journal is set to write back mode that provides better performance. In the experiment, we pin each user thread to a unique CPU core and increase the number of threads from 1 to 64. Figures report the throughput performance. In all the cases, the write performance and the scalability of the row RAID 5 far exceeds those enabled PPL or read journal. In detail, the write throughput of these read buffers is 1/7 of the row RAID 5, which is much lower than the performance of its underlying SSDs that only uses less than 25% of the SSD performance. Besides, the read-zero journal only achieves up to 8% throughput increase than that of a single SSD journal. It shows that the read journal could not combine multiple SSDs to promote the overall buffering performance. Then, to identify the cause of poor write scalability, we investigate the structure of popular read buffering mechanisms. The Linux read journal introduces a logging device upon primary read and buffers both data and parity updates. It presents a centralized log buffer model that abstracts a buffer device into a single log with logically linear address space. It uses a 12 log pointer to identify the current write offset on the single log. The incoming stripe writes and parity updates are sexually appended to the log by fetching the 12 log pointer without overriding its corresponding old data. To prevent concurrent requests to compete for the shared log pointer in the single log, they have to serialize IO comments to maintain the consistency of logging data. For example, Linux read journal uses an exclusive IO submission log for its log buffer to serialize all IO comments. The single log with serialized IO is upper bounded in its processing capability that falls to exploit the intra-parallelism of these fast SSDs. Compared to centralized log buffers, Linux partial parity logging conducts distributed parity log buffers that deploy multiple independent logs on each of the remember disks. However, PPL still serializes parallel stripe submissions and serially arranges IO submissions within each log to maintain data consistency. To solve the writing efficiency, we propose Mlog that builds upon parity-based reads to achieve high performance on buffering stripe writes. The goal of Mlog is to unleash the intro and inter-SSD's parallelism by optimizing the concurrent write buffering process, while diminishing the partial stripe write penalty. This figure illustrates the Mlog architecture that provides a stripe write buffer upon a primary reader read, like a Linux parity-based read, without changing the data layout of the read. To achieve the first goal, Mlog proposes a two-dimensional log data layout that physically partitions the global log buffer into multiple SSD zones in horizontal. Each SSD zone locates within a member SSD and is further divided into a set of independent sublogs in vertical. The capacity of a sublog is 1 GB by default. To exploit the intrinsic data parallelism among sublogs, Mlog set a fine-grained write lock for a sublog to serialize its requests. Then, to efficiently managing multiple sublogs, Mlog constitutes a set of independent sublogs located across different SSDs as a log group. Furthermore, to accelerate location queries for data reads and buffer reclamation, Mlog employs a hash-based log mapper that stores the data mapping relationship between Mlog and the primary array of each buffered request. To protect data upon device failure and system crash, Mlog supports to generate parities for the buffer data. And to this end, the sublogs within a log group could be categorized into data sublogs and parity sublogs. The former stores user stripe writes, and the latter stores parities for all user data in the same group. Parity sublogs of distinct log groups are dispersed among SSDs to avoid the parity write load becoming a bottleneck. Moreover, Mlog still faces new challenges in effectively managing multiple log groups and scheduling logging requests. To this end, Mlog proposes a spatial separation approach that schedules part of the log groups to serve front-end requests while dynamically reclaiming other groups in the background. The log groups is said to have three runtime states: active, flashing, and idle. An active log group is set to serve buffer requests. When being full, it switches to the flashing state to execute a reclamation in the background and will go into the idle state after reclamation. To assign the front-end requests, Mlog presents a two-phase write allocation method that evenly redirects incoming writes to different log groups and sublogs to provide concurrent and balancing logging writes. Mlog first hashes an incoming write to a log group according to its stripe number, where the stripe ID is the logical stripe number of the primary read. This hash-based allocation has three advantages: reaping the intra-SSD parallelism, less scheduling overhead, and better space locality for buffer data. It means that requests targeting a same read stripe would be redirected to a same active log group, compared to an intuitive approach of randomly redirecting requests to log groups. And this method improves the efficiency of buffer reclamation. Second, within the selected log group, the scheduler further employs a capacity-aware sublog selection method to equally split and distribute user requests across multiple specified sublogs. A small size request will be written to the tail sublog with the lowest capacity, while a large size request will first be split into several chunk size aligned subwrite requests. This method utilizes inter-SSD parallelism to handle large requests by request splitting while balancing capacity usage across various sublogs. Mlog monitors all the log groups' capacity. If the average capacity of its content sublogs exceeds a threshold, it will merge and flush buffer data to the underlying read. Mlog uses a log mapper to accelerate buffer reclamation. The log mapper allocates a fixed region for each active log group to store all the correlated request metadata in memory. It proposes a two-level indexing structure to store the metadata at the read stripe granularity. It contains a high concurrency hash table as a first-level index, and each hash entry corresponds to a stripe head structure that locates a physical stripe of the primary read. And each stripe head contains a second-level arm list to store all request metas corresponding to the stripe in order of arrival time. During the buffer reclamation, simply flushing buffer writes would induce numerous partial stripe updates to the primary read. And to solve this problem, Mlog had to first merge logging data into full stripe writes. Since the log mapper already stores and indexes request metadata at the stripe granularity, Mlog could access the log mapper to fetch stripe heads of the corresponding log group. Then it iterates the arm list to read buffer data in sublogs and merges them into full stripe writes in memory. In addition, Mlog has assigned requests targeting the same read stripe to the same log group in the two-phase allocation, thus preventing inconsistent stripe states due to different reclaiming orders. We run all experiments on server and use three types of storage devices with their details described in the table. We evaluate Mlog, Linux MD RAID built on 6 SSDs, and Linux read-write buffer mechanisms built on the primary RAID 5. We dedicate less than 50 GB of the MD space for deploying Mlog. The capacity of a sublog is 1 GB, and each SSD has 8 sublogs. We also compare Mlog with eplog and LDM, and set the same SSD footprint of them. We use both micro benchmarks and select 3 representative block traces from Microsoft, Alipangu, and FileBench as trace-driven macro benchmarks to evaluate Mlog. In the micro benchmarks, the last figure reports the write throughput of MD and 5 read buffering mechanisms. The throughput of Mlog exceeds that of other write buffers. This is because it reduces the overhead of I/O serialization on handling parallel log writes. The below figures show the average latency results. The y-axis is set to log scale. Mlog reduces up to 90% average latencies from MD because Mlog mitigates frequent data and parity block accesses induced by partial thread writes and utilizes a high sequential write performance of SSDs through the logging manner. Moreover, Mlog does not affect read performance, and the average read throughput differences between MD and Mlog is less than 4%. For the macro benchmarks, figures show the throughput performance of Mlog and the other 4 popular read buffers over time. Mlog achieves up to 4 times higher throughput and shortens the total running time by up to 70% than LDM. Mlog also has at least 69% lower average latency, and the median latencies of Mlog are almost 2 orders of magnitude lower than regional and partial parity logging. We also evaluate the sensitivity of Mlog to different types of storage devices. The results show that Mlog is adaptive to various types of storage devices, even including the often persistent memory. At last, we evaluate the performance scalability of Mlog built on different numbers of SSDs. The throughput of Mlog with 6 SSDs increases by 2 times than that with 3 SSDs, because it evenly schedules requests across underlying SSDs based on its multi-log architecture and leveraging the high parallelism inherent among multiple SSDs. Here we conclude the presentation. We experimentally reveal that the read-write buffering mechanisms built on parity-based reads can't fully exploit the potential of fast SSDs due to the architectural drawback of the existing centralized log buffers. And to this end, we propose a highly parallel read-write buffering Mlog to efficiently handle parallel stripe writes. Mlog provides a 2-dimensional data layout and introduces a 2-phase request allocation to provide parallel I/O processing by exploiting the inherent I/O parallelism. Besides, Mlog generates parities for the logging data to enhance reliability. Through evaluations, Mlog is shown to constantly outperform popular read buffer mechanisms in write performance. More details like the async log parity submission method and the detailed request allocation policy are shown in the paper. And that's all the presentation. Thanks for your listening.